Good afternoon, everyone. Today we are going to apply what we have learned during the last lectures, and we are going to extend the way how we do the layout to design the Cascode Amplifier. During the last lectures, we have done the schematic for a very common emitter amplifier. We have also done the layout, and the layout is based on the model from the manufacturer, NBN 555WDN. So this is the NBN Spice model. Today I'm going to use the same model and extend the original common emitter amplifier to Cascode Amplifier design. We need the Cascode Amplifier designs in order to generate a broader bandwidth. So before doing this, we are going to do the design in LT Spice first, just to get the feeling what sort of resistor we need. Now this is the design of the Cascode Amplifier. Here I use 2K as a resistor connected to the collector of the Q1 transistor, and in a bias I only use 3 volts to bias the whole circuit. Here there's something we have to pay attention to. We need to develop a series of resistors in a way that we can bias the base of 2 transistors correctly. In our case, I have used 0.8K for the bias for the base of Q2, and I have used a similar amounts for R1 and R2, but of course you can also scale this resistor blocks by 10. In this case you have 18K here, 5K here, and 8K here. But if you use that much resistance, then you need to use a log of chip area to design this simple Cascode circuit. So I'm not going to waste too much space. I just use 0.8K, 0.5K, and 1.8K. As long as you can keep this ratio, then you should be able to do the right job. Now, if I simulate this circuit, I will get a really nice frequency response, and the bandwidth goes from 2K to 12 meg, 2 kilohertz to 12 megahertz. Now, here 18K is equivalent to 29 unit in terms of the length, and 0.5K is equivalent to 8 unit in terms of the length, and 0.8K is equivalent to 13 units. 2K is equivalent to 32 units in terms of the length. So we try to remember this, and then during the times of layout, then we will put the right geometry for each resistor. Before doing this, we are going to design a Cascode amplifier in electric VLSI. So create a new cell, Cascode Amp, which is the name we are going to use for the Cascode amplifier. Now we have got the Cascode amplifier schematic, and then we create a layout as well. The name will be the same. Now, during the last lectures, we have already developed a NPN cell. Now we are going to use the same cell. And we are going to use N-well resistor as the resistor for the biasing network. I'm going to rotate it. Now for this resistor, I will use 40 unit for the width, and then as I have already explained, the length should be around 32 units, and this resistor value should be 2K. And this resistor value again, the width is around 40 units, and the length should be 29. This will end you up with a resistance around 1.8K, and this one again we use 40 as the width of this resistor, and the length should be 8 unit, and for this one the resistance should be around 5K, 500. And this one Again, we use 40 for the width, and the length here should be 13 units, and this will end you up with a resistance 800 ohm. Now the next thing is to connect the wire. And this one is connected to here. And then we are going to add some pins, and for this one is VDD, actually VACC. And this will be the input voltage. As I have already explained in the last lectures, it's very difficult to come up with a large value of capacitance in integrated circuits. So in this case, we connect a so-called input pin here. But this input pins, the user of this circuit will have to add a discrete capacitance, discrete capacitor, to connect the input voltage into this pin. We call it V in, and we call this terminal VM. This is just the name, and this one is the output. We call this Vout. And we also need a pin for the ground. G and D. Now basically we have almost everything, except that we need to add some capacitor in our simulation, in the schematic. So let's see what we have done in the last lectures. We have got this so we are going to copy and paste this spice text. Spice text, as you say. we need the input capacitance to connect VV in and V in, which is the input pins of the chips, to 100 microfarads, and another capacitance for the output. And this VV out is another artificial pins. And then we also need another capacitor, VM, CM, VVM, and then VM, 10 micros. Now the input voltage is okay, and the voltage supply, I have used 3 volts. I think that's fair enough now. Let's see what we are going to get. First of all, we need to do some cleanup, and then we do DRC, design rule check. Let's see if we have got any error. So far so good. Now we are going to do spice simulation. Okay, it looks good. And then we are going to measure the voltage gain. So this is the frequency response we are going to get from this circuit. Now the next step is to do the layout. So we are going to the layout window. Again, we need to use what we have done during the last lectures. We have got this. And we need one more. And we need the 4 resistors. This resistor will be N-well resistor again. N-well resistor. So this is not the library we are looking at. We should look at MOSIS. N-well resistor. we need 4 different values of the envelope resistor. This one will be 40, 30, 13, and the resistance here should be 800. And then we need another one. The width here is again 40 units, but the length should be 8 units. In this case, it will end you up with 500 ohms. We need one more. And 40, and the length here should be 29, which will give you around 1.8K. And then we need one more here, which is the last one. The value here should be 40 units for the width, 32 units for the length, and the resistance should be around 2K. Now we are going to mirror this. Right now the emitter is here, the base is here, but I want the base to be on the left side. So I'm going to mirror this record from left to right. Again, we are going to do the same from left to right. So now the emitter of both transistors are in the right side. Yeah, I think this is about right now. So okay, let's try it. Yeah, I'm going to increase the track width, the conductor width to 35 units. And I'm going to do the same here. I want it to be 45 in terms of the width. And this one should be 30. This will be too big. 28. Maybe 28. Plan is right now. Okay. I will make it 20. Again, 20. 15. See what happens. It's too big. And then I will increase the width in a similar manner. Looks okay. Okay, now apparently we are heading there. Now let's give some small metal and then here let's make it thinner. Okay, looks good. And this one is VM. VM. VIN. Then let's delete this one. Let's see if we can do that. And this one is VO. Now obviously you need a pins here. VCC, and then we reduce the length. Don't worry about it now. So this is the layout we have got. It's a bit large. Now we are going to use the same spike stack to simulate this layout. Now we got the same, exactly the same simulation result. Now the next thing we are going to do is to do layout word schematic check. Here we got NCC schematic layout views. So this is the option we are going to choose for the layout word schematic check. Let's see if we have any error. Exports match, topology match, size log check. So everything is okay. So this is the way how we accomplish, how we complete the analog layout. I have not optimized the area, but this is something you can do. Let's see. I'm trying to see if I can shrink the layout a little bit. Apparently I can do that. VM now let's check VLSI low error, NCC also okay. So this is the layout you are going to get from your homework.